To start with, we will consider the equation of motion plus kx equal to 0 and look at its solution, represent it by a phasor diagram. After that, we are going to introduce damping into the system and see how it changes the motion, and after that we are going to study the forced oscillations of these systems when the system is subjected to an external force in addition to its own force, like the spring force that it experiences. So to start with, let us take our prototype spring mass system and let us measure the displacement from the equilibrium point as x, and the equation of motion, as we have been saying, is mx double dot plus kx is equal to 0. And we have seen in the past that to solve such an equation, we assume the solution of x to be of the form e raised to lambda t, substitute it in the equation, then we get m lambda square plus k e raised to lambda t is equal to 0, which is true for all the times. Since it is true for all the times, I must have lambda square is equal to minus k over m, and therefore lambda comes out to be plus minus I square root of k over m, where I is equal to square root of minus 1. So I have two solutions for the second order differential equation mx double dot plus kx equal to 0. The two solutions are e raised to I omega 0 t and e raised to minus I omega 0 t, where I am writing omega 0 to be equal to square root of k divided by m, so that lambda that I wrote earlier can be written as plus or minus I omega 0. The general solution for a second order equation, therefore, is going to be xt, which is a linear combination of these two solutions, a e raised to I omega 0 t plus b e raised to minus I omega 0 t. Since I know that the displacement xt is real, therefore I should have in the solution xt, which I am writing as a e raised to I omega 0 t plus b e raised to minus I omega 0 t, and xt is real, and therefore b must be equal to a star. So in general, a is complex, but for xt to be real, I should have the solution of the form this equal to a e raised to I omega 0 t plus a star, where a star is the complex conjugate of a e raised to minus I omega 0 t. That is the general solution. Since it involves complex quantity a and a star, let me write it in a slightly different form, writing a as a real plus I times a imaginary. When I substitute this, I get xt is equal to a real plus I a imaginary, and I can open up e raised to I omega 0 t as cosine of omega 0 t plus I sine omega 0 t, plus the second term, which is a real minus I ai, where ai is the imaginary part, cosine of omega 0 t minus I sine of omega 0 t. When I open this up, the final solution that I get is going to be xt is equal to, which I wrote as a real plus I ai cosine omega 0 t plus I sine omega 0 t plus a real minus I a imaginary cosine omega 0 t minus I sine of omega 0 t will be equal to 2a real cosine of omega 0 t minus 2a imaginary sine of omega 0 t. If I call these constants c and minus 2ai d, I can also write my solution as xt equals c cosine omega 0 t plus d sine of omega 0 t. That's another way of writing the solution of the equation mx double dot plus kx equal to 0, which is equivalent to the solution that I got earlier in terms of e raised to I omega 0 t and e raised to minus I omega 0 t. So, what we have learned so far is, given this equation for a spring mass system or the motion of a particle about its equilibrium point, its motion is going to be described by the displacement xt is equal to a e raised to I omega 0 t plus a star e raised to minus I omega 0 t, or equivalently c cosine of omega 0 t plus d sine of omega 0 t. And third way, again you can write this as some amplitude times cosine of omega 0 t plus a phase constant called phi, or also if you like sine functions, I can write this as sine omega 0 t plus a phase constant called phi. It's our choice how we want to represent the solution, where a is going to be, in this case, square root of c square plus d square, and depending on whether I write it as cosine omega 0 t plus phi or sine omega 0 t plus phi, the sine of phi is going to be c over a, and cosine of phi equals d over a in the case when I write this as sine of omega 0 t plus phi. So, we have in the motion two constants, a real, a imaginary, or c or d, or a or phi, and these are determined by the initial condition of the motion, as we will see. Let us try to see how this motion looks. So, let me just write xt is equal to a cosine of omega 0 t plus phi. How this motion looks? In general, this would look something like this, where this maximum distance is going to be a, the time between this and this two equivalent point is going to be t is equal to 2 pi over omega 0, and this initial displacement is a cosine of phi. How about the velocity of the particle? That's very simple. Since I am given xt is equal to a cosine of omega 0 t plus phi, the velocity x dot t is going to be minus omega 0 a sine of omega 0 t plus phi. How about the acceleration? X double dot t is going to be minus omega 0 square a cosine of omega 0 t plus phi. Let us plot them and see. So, as I said, xt in general would look something like this. X dot is going to be slope of this, and it's going to look something like this. This is x dot. You can see here the slope is positive, that means the velocity is positive. At the maximum displacement, the velocity becomes 0. As the spring mass system, the mass goes to its maximum displacement, it stops momentarily, then it starts coming back with negative velocity. Again, when it passes through the equilibrium point, when the displacement is 0, its velocity is maximum, it is going back with maximum speed, and then its speed starts slowing down, it reaches 0 again when it reaches the other extreme, and so on. The acceleration is going to be negative of the displacement times omega square. So that's going to look something like this. I have not shown the magnitudes, I have just shown how in general the velocity and the acceleration are going to look. Black one obviously is the displacement. As the first example of solving this equation, let us go back to our spring mass system and let us take mass of the block to be 1 kilogram. Let us take K to be 16 newtons per meter, and let us first displace the mass by 0.05 meters, let us say to the right, and leave it. Let us see what happens. So in general the solution xt is c cosine of omega 0 t plus d sine of omega 0 t, and as I said earlier, c and d are determined by the initial conditions. Initial conditions given are that x at time t equal to 0 is 0.05 meters, and since we have just released it, x dot at t equal to 0 is 0. When we substitute this condition, I get x at 0 is equal to 0.05 should be equal to c plus d times 0, or I get c equals 0.05. We have determined one of the coefficients. For the second coefficient, I take derivative of xt, which is going to be equal to minus omega 0 c sine of omega 0 t plus omega 0 d cosine of omega 0 t, and at t equal to 0 this quantity is omega 0 d, and this is given to be 0. This implies d is 0. So in this situation, when we took the particle and took it to a maximum distance and left it, the solution looks like xt is equal to 0.05 cosine of omega 0 t. If I plot it on xt plot, it will look something like this, where this distance is 0.05. If I were to plot the velocity of the particle, I will take the derivative, and that would come out to be x dot t is equal to omega 0 times 0.05 sine omega 0 t with a minus sign here, and that would look like this. Initially the particle is moving towards the left, it has negative velocity, the velocity reaches maximum and then it slows down and then goes to the other side. Here omega 0 is equal to square root of k over m, which is 16 over m equals 4 radians per second, so that the maximum speed, which is 0.05 times 4, is 0.2 meters per second. So to see it again, this is how xt looks when plotted, and this is how the velocity looks, where this maximum, I have not drawn it to the scale, is 0.2 meters per second, and this maximum is 0.05. Let us take a different set of initial conditions and see what answer do we get. Now let me take the same system whose solution we have already determined is xt is equal to c cosine of omega 0 t plus d sine of omega 0 t, where omega 0 is equal to square root of k over m is equal to 4 radians per second. Let me take something with which I can hit the block, and let me give it an initial speed of 0.1 meters per second to the right from the equilibrium, so that I have x0 is equal to 0 and x dot 0 is equal to 0.1 meters per second. With this, I will get 0 is equal to c plus d times 0, which gives me c is equal to 0. So this time c is 0. On the other hand, x dot at 0 is given to be 0.1 meters per second, and this would come out to be omega c sine omega 0 t, and this is already 0 because we have seen c is 0, plus omega 0, this is with a minus sign, d cosine of omega 0 t, and this tells me that 0.1 is equal to omega naught we have determined to be 4 d at t equal to 0, and therefore d is equal to 0.1 over 4, which is 0.025. In this case, therefore, when I take the spring mass system and give it an initial velocity at the equilibrium point of 0.1 meters per second, the solution comes out to be 0.025 sine of omega 0 t. When plotted against t, the solution would look like this, where the time period, that is, this is t, this is xt, the time from here to here is 2 pi over omega 0, which is 2 pi over 4, or pi divided by 2 seconds. The velocity in this case, x dot t, is going to be 0.1 cosine of omega 0 t, as you can see easily by differentiation, and therefore when I plot it, it will look something like this, with the maximum being 0.1 meters per second at t equal to 0, which we saw, with which we really hit the mass in the beginning. Again, you can see initially the slope is positive and therefore velocity is positive. The slope is decreasing slowly, so velocity keeps going down, crosses 0 at the maximum displacement, and then goes negative.